Pleased to introduce our last speaker, who is Elizabeth Tatum from UIUC, and who will tell us about splitting BP angle brackets to smash BP angle brackets to at primes at least 5.
Okay, sorry, I realized I forgot to mute myself. We were just thanking the local organizers for all their great work. Yeah, sorry about that. So yeah, maybe before I talk about how to split BP2, smash BP2, at primes greater than or equal to 5, I'll say briefly like why one might be interested in doing that. Oops. Apparently, okay, cool, sorry. All right, so a central question in stable homotopy theory is to ask, like, what are the stable homotopy groups of the sphere? And, well, that turns out to be intractable, but tons of interesting structure and patterns have been found. This has also really been like a driving force for other developments in the field, like lots of tools and techniques have been developed. And one family of tools that can be used to study this structure are called the R-based atom spectral sequences. So if we take R to be like any reasonable connective ring spectrum, there will be an R-based atom spectral sequence. So this is a spectral sequence whose E1 page has, sorry. Oh no, I'm sorry. I'm sorry, I just wanted the pencil so I could point. Just checking if we're awake. Yeah, so sorry. Okay, so the E1 page, which is hopefully right side up for all of you now, consists of the homotopy groups of R smashed with itself many times, and that should converge to the homotopy groups of the R-completed sphere. So some sort of approximation of the homotopy groups of the sphere that depends upon the choice of R. And if this is the E1 page, presumably we would want to know about the E2 page next. And if the spectrum R is flat, meaning if the R homology of R is just a sum of copies of the homotopy groups of R with appropriate suspensions, then the E2 page has this nice algebraic description. So that's cool because then you get the E2 page for free. So like, for example, if R is the mod P Eilenberg-MacLane spectrum, that will give you the classical atom spectral sequence. So I think this is one that like more people are more likely to have seen more of. So the E2 page here, it's X'd over the mod P homology of the mod P Eilenberg-MacLane spectrum. That's the dual Steenrod algebra. Then the homotopy groups of the mod P Eilenberg-MacLane spectrum should be FP. And so that should converge to the homotopy groups of the P-completed sphere. Another example that's pretty classical is the Adams-Novikov spectral sequence, where you're taking R to be the Brown-Peterson spectrum. And so these are both really great choices of ring spectra. For one, the E2 page has an algebraic description, which is great. They contain tons of information about the homotopy groups of the sphere. But maybe one big drawback is that it's really difficult to compute further differentials. I guess another thing I should say too is that even though it's really nice that these E2 pages are algebraic, they're still extremely complicated. They don't have like a closed form. So it can be helpful to consider some other choices of ring spectra as well. So maybe a pair of ring spectra that have both been very useful. One being the one being BO, the real connective K-theory spectrum. And then at P equals 2. At odd primes, BP1 has been sort of played a similar role. So something really great about these spectra is that they make it easier to extract the V1 periodic structure in the homotopy groups of the sphere. So it's expected that pi star S should be organized into these like V1, V2, etc. periodic patterns. And if you somehow understood all of those Vn periodic patterns and like how those fit back together, then you would like understand pi star S. And these two choices of spectra really highlight the V1 periodic structure. Another really nice thing about these choice of ring spectra is that in a certain range, not for like the whole spectral sequence, but just there's a vanishing line, and so in a certain range, they collapse at the E2 page. So once you have the E2 page, you have a lot of information. But one really big drawback is that these spectra are not flat. So you can see we wrote the E1 page and not the E2 page. So just getting to the E2 page is a lot of work and requires a really good understanding of the E1 page. So I said that these had been like very useful. So here's some examples of what they've been used for. So the BO-based atom structural sequence was used to show that the telescope conjecture holds at height n equals 1 and the prime 2 by Mahawold. And just more generally, the BO-based atom structural sequence for the sphere has been like completely computed through the 40 stem and I think a little bit past. And so I think that's sort of the most efficient description of like the V1 periodicity in the two local sphere. Then the BP1 based atom spectral sequence, I think maybe hasn't been like quite as used quite as much, but there are some really great results with that as well. So one result by Gonzalez gives bounds on the P torsion of any class that's not detected in the image of J. So a little bit more about what the truncated Brown-Peterson spectra are. So the homotopy groups of like the Brown-Peterson spectrum itself are generated over the P local integers by this like infinite set of generators. So the homotopy groups of the n-truncated Brown-Peterson spectrum, this is just a spectrum that's been constructed to just be generated by the V1 through the n generators. So when n is really small, these spectra have some other familiar names. So BP0 is actually the Eilenberg-MacLane spectrum for the integers localized at P, because its homotopy groups shouldn't have any of those VI generators. BP1 is complex connective K-theory localized at 2 when the prime is 2, and it's the Adams L summand of K-theory when the prime is odd. Then BP2, sort of analogously to how BP1 is related to K-theory, BP2 is related to topological modular forms, but the relation is a bit more complicated. So BP2 is a form of topological modular forms with level structure at the prime 2. At the prime 3, there's a certain spectrum of topological automorphic forms, which is like a generalization of topological modular forms. That's an E-infinity form of BP2. At primes greater than or equal to 5, no E-infinity structure is known to my knowledge, but BP2, just like as a spectrum, is a summand of TMF. So that's another reason to be interested in BP2 if you like topological modular forms and things like that. So the BP1 based atom spectral sequence, as we said, highlights the V1 periodic structure. And it's expected that a BPN based atom spectral sequence would highlight the VN periodic patterns in a similar way. But kind of the same drawback as BP1, BPN is not flat. So in order to actually use a BPN-based atom spectral sequence, you need a really good description of its E1 page. And breaking BPN/BPN into like sums of finitely generated BPN modules can help to accomplish this. And that's the sort of strategy that was used in order to actually work with a BO-based or BP1-based atom spectral sequence. So before I talk about like how we break these smash products into like these finitely generated sums, I need to talk about a class of spectra called Brown-Gittler spectra, which are like very important for this sort of thing. But I guess so first what we'll do is talk a little bit about like the homology of BPN, and then kind of talk about Brown-Gittler comodules, and then we'll talk about how we realize them as Brown-Gittler spectra. Or not how we realize them, but we'll talk about how some of them are realized. So the homology of BPN, I'm just going to say anything explicit in terms of odd primes, but you can absolutely tell this story at the prime too as well. So if P is an odd prime, the dual Steenrod algebra is the mod P homology of the mod P Eilenberg-MacLane spectrum. It has this polynomial piece and it has this exterior piece. So if we let E of n dual just be the exterior algebra on these first tau naught through tau n generators, then we're going to be particularly interested in this A mod mod E of n dual, which is a subalgebra of the dual Steenrod algebra. And the reason we're interested in this is that the homology of BPN is A mod mod E of n dual. So now we want to define Brown-Gittler comodules. So I'm going to do a slightly weird notation thing and call BP minus 1 the mod P Eilenberg-MacLane spectrum, so that we can say that the homology of BP minus 1 is the dual Steenrod algebra. Sorry about that. So these Brown-Gittler comodules You have them for every I greater than or equal to -1. They should be a family of comodules, n sub I of k, k and n, such that they're giving you like an increasing filtration on the homology of BPI. Each of these n sub I of k's is finite. And then for every n greater than or equal to 0, you can take the homology of BPN, tensor with itself, and split this as the sum of the homology of BPN tensored with a sum of these Brown-Gittler comodules from one height down. And I guess I didn't actually say what Q is here. Q is 2 times P minus 1, but it doesn't matter very much for this. But yeah, the point is that we've taken the homology of BPN tensor with itself, and we've split it as a sum of the homology of BPN tensor with something finite. So if we could realize this on the level of spectra, that would be very helpful. It's also kind of cool that we've in some sense shifted down a height here. So in order to actually realize this sort of splitting, we need to at least know that a spectrum with the appropriate homology exists. And so for I between -1 and 2, the Brown-Gittler spectra have been constructed by many contributions from many people that actually realize these comodules. So for just n-1 of k, we were just looking at this filtration just on the dual Steenrod algebra itself. These are due to Brown and Gittler at the prime 2, and odd primes due to Cohen. Then for n0 of k, this is Mahowald, Kane, and Shimamoto. These LKs are Gross-Jones-Mahowald, and BP2k is due to Klippenstein. It's not actually yet known whether or not they exist for higher heights. But for small n, where we know they exist, we can try to realize this splitting. And so that's been done at low heights. So for BP0, which remember is actually the p-local Eilenberg-MacLean spectrum, this is due to Mahowald. For BP1 smash BP1, this is due to Kane. So then you might think, okay, for BP2 smash BP2, it probably works out as well. But I want to touch briefly on like a sort of parallel story to this that might give you pause. So you're still here. So you can tell sort of the same story about looking at where instead of looking at this subalgebra E of n and looking at A mod mod E of n dual and getting these algebraic splittings, you can look at a different subalgebra called A of n at the prime 2 and look at A mod mod A of n. And so you get everything is like very analogous. And so for sort of the height 0 sort of thing there, sorry, the height 1 sort of thing there is BO smash BO. And you can realize that analogous splitting. That's due to Mahowald. So then you might think, okay, the height 2 thing there is TMF smash TMF. In homology, this absolutely works. You get an isomorphism. But Davis-Mahowald showed that the homotopy groups of the left-hand and right-hand side here do not agree. Also, I should say these are all splittings up to P completion. Okay, so it's conjectured that however, like even though you see this Davis-Mahowald thing, they were able to show that you don't have the equivalent splitting at height 2. For BP2 smash BP2, it's still conjectured that this works at all primes. And so one piece of evidence towards that conjecture is Culver's result that the left-hand and right-hand side homotopy groups do agree. So that doesn't necessarily tell you that you get a spectrum level splitting, but at the very least, you're not running into the same issue as you would for TMF smash TMF. And so in my thesis, I've shown that for primes greater than or equal to 5, this splitting actually can be realized up to P completion. So I think I'll spend the remainder of the talk like outlining how I approach that. So the general approach that I took to constructing this splitting is to lift this a certain family of maps, theta k, that go from like appropriate suspensions of the Brown-Gittler spectrum into the homology of BP2 tensor with itself to a map of spectra. And so the reason for that is that no, sorry, this I want to move. Okay. So the reason for that is that it's like fairly standard algebra to show that if you could realize this map here, and then you took this composite where you start from BP2 smash LK, and you take the identity on BP2, the appropriate lifting on LK, then you land in 3 copies of BP2, you multiply the first two copies together using the standard multiplication, and then you land at BP2 smash BP2. The sum of these maps here will induce an isomorphism in homology. So that tells you that you're getting equivalence after P completion. And so then you would be done as long as you can actually realize these maps theta k. So actually showing that the maps theta k can be realized is like more involved. So I'll talk about that. So the approach that I took is to use another atom spectral sequence. So each of these maps theta k here, we can think of as being a class in the E2 page, which is x'd over the dual Steenrod algebra from the homology of the appropriate Brown-Gittler spectrum into the homology of BP2, tensor with itself. And so basically, if this class theta k survives a spectral sequence, then it should generate an appropriate map from LK to BP2 smash BP2. So one thing I want to do sort of immediately with this spectral sequence is use the standard change of rings. So the homology of BP2 here is A mod mod E of 2 dual. So that lets us rewrite this as instead of x over the dual Steenrod algebra of like mapping into two copies of the homology of BP2, just x over E of 2 dual mapping into one copy of the homology of BP2. So that's a little bit nicer. So then we want to ask, does theta k lift? So theta k lives in S and T degree 0. The differential increases the topological degree, or sorry, it increases the homological degree by R. So I guess first we want to ask, are there any differentials hitting theta k? And right away you can say no, nothing lives in negative homological degree in X. But showing that there are no non-trivial differentials leaving theta k is a lot harder. So we'll say that class X in this E2 page is going to be a potential obstruction, just if it lives in a degree where it would be possible for a differential off theta k to hit it. So we don't really need to understand like everything about this X term. We just really need to understand the potential obstructions, because the idea is that oh yeah, please.
What's the relation between S and K
In the third bullet? Oh yes, sorry. So Doug was asking, what's the relationship between S and K in the third bullet? Yeah. So yeah, that's a good question. So LK here is just one of the Brown-Gittler spectra, and we want to show this for all K in N. We need to construct these maps. Then S here is just the homological degree in the atom spectral sequence. Oh, sorry, are you saying, are you asking about like how S, like the degrees in which, like how far up you could have a potential obstruction increases with K?
I'm asking if there's any, can S be anything or is it controlled by K?
Oh yeah, thank you. Yeah, so it's controlled by K. Yeah, so for each K, you should have finitely many potential obstructions. Yeah, so I don't remember like off the top of, I don't know that I ever like worked out like a specific function for it. But yeah, there's like, you're only gonna have like finitely high S for each K. Yes. Yeah, thank you. Yeah, any other questions while I'm paused? Okay. Yeah, so the idea is that if we can show that all of these potential obstructions survive, then that will tell us that they can't have been hit by a differential off theta k. So then theta k itself must also survive. So in order to actually like show that the potential obstructions survive, we're going to actually use another spectral sequence. So the idea here is that we're going to use a type of universal coefficient spectral sequence. This is Buda-Robinson. So if we look at X over BP2 star, BP2 star LK, BP2 star BP2, this should converge to the same thing as the atom spectral sequence we were looking at. So we can draw this like fun little diagram. But what's really interesting here is that these two spectral sequences, even though they're converging to the same thing, have really different filtrations. So one thing to notice here is that if you're looking at X over BP2 star has global dimension 3. So anytime the homological degree here is greater than 3, this is just 0. Whereas in the atom spectral sequence, even though for like a given k, you'll only have the potential obstructions like going up like finitely far in S degree, just in general here, you can have like classes in arbitrarily high S degree in the atoms filtration. So we're going to play those two very different filtrations off each other to show that the potential obstruction survives. So maybe to be like a little bit more specific, what we'll do is say we have a class X in the universal coefficient spectral sequence. It's non-trivial, and we know that it lifts to form a class here. Then there must have been some corresponding class in the atom spectral sequence that matches it. So what we'll do basically is show that there's some family of classes here that's going to survive the universal coefficient spectral sequence. Then we'll look at what possible classes in the atom spectral sequence could match it, and it will turn out that the potential obstructions must survive in order to match the classes we're getting from the universal coefficient spectral sequence. And so I got the idea for doing this sort of comparison from a paper of Klippenstein's. And in his paper, he was able to just compute like the E2 page of the universal coefficient spectral sequence very explicitly. Same thing for the E2 page of the atom spectral sequence. But he was doing work at height 1 where it was a bit, I think, more feasible to get these things very explicitly. So what I did instead of computing these things directly is used yet another spectral sequence as a bridge between the two of them. So I'll actually say like what these things are in just a moment. But basically the idea is that on the left-hand side here, I have, I guess here I have the E2 page of something called the hypercohomology spectral sequence. In this case, it's actually converging to the E2 page of the atom spectral sequence. And then in this very specific instance, it turns out that the E2 page of the hypercohomology spectral sequence will be isomorphic to the E2 page of the universal coefficient spectral sequence. So now I'll say a little bit more about what these things actually are. So the hypercohomology spectral sequence is like a classical spectral sequence due to Cartan-Eilenberg. And I should say it's actually stated by them in terms of modules, but I'm using an equivalence of categories between E of 2 dual comodules and some modules over an exterior algebra. So if we take these two comodules and we let G be the right-derived functor on Homs out of E of 2 dual, and then we're going to let P of 2 here for like polynomial denote G applied to FP, because that will just be the polynomial algebra on these generators over FP. Then Cartan and Eilenberg tell us that there's going to be this hypercohomology spectral sequence where we're starting from X over P of 2. We're taking X of M, X of N, and this should converge to X over actually these derived things of M and N. So now the left-hand side here looks like what we wanted, but the right-hand side still needs a little work. But it turns out that as it follows from causal duality, that if M and N are sums of finitely generated modules, then actually we can rewrite the target here as just X over E of 2 dual of M and N. So that's like very briefly how we get this top line here. Then I think for the sake of time, I'm going to be, not that I was super precise about the top line there, but I'm not going to go into a ton of detail about the isomorphism here. But I think sort of the thing to notice is that there's this atom spectral sequence. We've had a lot of atom spectral sequences here, but here's another one, where if I want to know about the BP2 homology of some spectrum X, I have an atom spectral sequence here. I can do a change of rings. And say that this is FP into H star X. And this should converge to the BP2 homology of X. And so if you look up here, this X E of 2 dual here is the E2 page for the atom spectral sequence converging to BP2 star BP2. Then this X term here is the E2 page for the atom spectral sequence converging to BP2 star LK. And then this P of 2 here actually is the E2 page for the atom spectral sequence converging to BP2 star. Then we can use Culver's result, which tells us that these atom spectral sequences here are going to collapse the E2 page, so that at least gives you an isomorphism between their associated gradients. Then we use the fact that the atom spectral sequence is multiplicative. and just say that like basically like the P of 2 structure up here is determining the BP2 structure down here. And then finally, we check that there's no like surprising hidden extensions. You certainly have an extension from V0 to P, but there's no more extensions past that or besides that. Okay, so then okay, so we have this square, and we want to, I said we were going to use it to analyze the potential obstructions. But in order to actually do that, I want to split it into like a sum of 4 smaller squares that are easier to manage. So I'm actually going to use a different decomposition of BP2 smash BP2 and BP2 smash LK to do that. So it's the theorem of Culver's that if X is BP2, then there's going to be a splitting of BP2 smash BP2 into these 2 pieces with the following properties. So this V here should be a sum of mod P Eilenberg-MacLane spaces. And this C here should be V2 torsion free and concentrated in even degrees. And if you look at the paper, I think it's just dated for BP2 smash BP2, but BP2 smash LK is like very immediate from that. Okay, I want to use the splitting, but this is where the prime being greater than or equal to 5 is going to come in. I need it to be a BP2 module splitting. So what we can do is use this theorem of Smith's, which says you can construct this generalized Moore spectrum that's a sphere mod P V1 V2 with the and it'll have the property that the mod P Eilenberg-MacLane spectrum is BP2 smashed with this thing. So as a corollary to these 2 things, we can show that for primes greater than or equal to 5, Culver's splitting is a BP2 module splitting. And so then just a little notation thing that I'll do, BP2 smash BP2 is, I'll just say C wedge V with no decoration, and BP2 smash LK, I'll just write the K there. So, okay, now we want to use this to split the square. But looking here, we have BP2 smash BP2, we just have LK. But that's why it's good that we said they are BP2 module splittings, because maps from LK into BP2 smash BP2 is going to be equivalent to BP2 module maps out of BP2 smash LK into BP2 smash BP2. So now you get that this is splitting as the sum of these 4 different pieces. And it follows fairly quickly for degree reasons that any of the potential obstructions are going to be contained in the atom spectral sequence converging to just this piece. And you can do this splitting throughout the square. Okay, so now we're just looking at the part that's basically we've gotten rid of all of the mod P Eilenberg-MacLane spectra. Okay, so then finally, I'll just say real quick a little bit about how we actually do this comparison. So the first proposition we use is that if we're looking at map at X out of pi star CK, that's going to be 0 for all U greater than or equal to 3. And that follows from pi star CK being V2 torsion free. So because of the differential increases the U degree by 2. So that tells us that the X1 line here, everything on the X1 line is going to survive this universal coefficient spectral sequence. And it turns out there's a lot of non-trivial classes on there. Then the next thing we show is basically for dimension reasons that this X1 line piece, so this X1 line here is going to be isomorphic as like an FP vector space to just anything that's in odd T minus S degree here. For degree reasons, in order for something to be a potential obstruction, it has to have odd T minus S degree. So then basically we're looking at this X1 line, all these classes generated by the X1 line. In order to account for them, we need a class to survive the atom spectral sequence. There's only one class for each of these. So everything that's an odd degree survives the atom spectral sequence. That includes the potential obstructions. The potential obstructions survive, so the theta k's survive, and we get the splitting. The end.
Questions for Liz?
Do you know anything about what the sort of -2 column